One of the most quietly influential operating systems in computing history is named after what's often called the worst movie ever made. Plan 9 from Bell Labs takes its name from Ed Wood's 1957 B movie, Plan 9 from Outer Space, a film so clumsy it became a cult joke. The researchers at Bell Labs borrowed the title with a straight face and a bit of self-mockery. If this grand new system flopped, at least they'd called their shot. The real Plan 9 wasn't a movie. It was a research operating system built in the 1980s and 90s at Bell Labs by many of the same people who created Unix and the C programming language. Internally, it was pitched as the system after Unix, the chance to redesign an operating system from scratch with 20 years of hindsight. It never became a mainstream product. You almost certainly don't run Plan 9 on your laptop or phone. But many of the ideas behind the systems you do use, from UTF-8 text to containers, to parts of Go, to how cloud services talk to each other, trace back straight to this oddly named, nearly invisible operating system. This is the story of how a joke-titled research project failed as a product, and quietly won as a set of ideas. To understand Plan 9, you have to picture Bell Labs in the mid-1980s. This was the Computing Science Research Center, the same group that had created Unix in the late 1960s and early 70s. Ken Thompson and Dennis Ritchie were still there. Rob Pike, Dave Prasato, Phil Winterbottom, Doug McElroy, Brian Kernighan. Names that, inside systems programming, carried an almost mythic weight. By the mid-80s, Unix had escaped the lab. AT&T had licensed it widely. Universities had taught a generation of programmers on it. Commercial offshoots like System Phi and BSD had spawned their own children. The result was success and ossification. The once small, elegant research system now existed as a tangle of vendor variants, each with its own extensions, bugs, and politics. Inside Bell Labs, Unix had become, ironically, too big to experiment on. Backward compatibility in standards like POSIX made radical changes difficult. Researchers who had once hacked on the OS between coffee breaks now found that the cost of real change was enormous. So a question began to loom over the systems group. If we started over today, with what we've learned from Unix and from distributed computing, what would we build instead? Plan 9 was their attempt to answer that question on real hardware, not just in papers. The seeds of Plan 9 go back to around 1984. Rob Pike and Ken Thompson were already talking about a new system that could treat an entire network of machines as one coherent environment, glued together by a single uniform protocol. Throughout the 1980s, they and their colleagues ran a series of small experiments: prototype file servers, experimental kernels, odds and ends of distributed infrastructure. These weren't yet a full operating system, more like a sketchbook of ideas. In early 1989, they decided to build the real thing. Bell Labs ordered dedicated hardware, and the team began building a serious write once, read many, or WORM, file server and a new kernel to go with it. By the end of that year, Plan 9 was taking recognizable shape. The core founding group included Ken Thompson, Rob Pike, Dave Prasato, and Phil Winterbottom. Dennis Ritchie, by then heading the Computing Techniques Research Department, provided air cover and oversight. Over the years, a remarkable cast drifted in and out. Brian Kernighan, Tom Duff, Doug McElroy, Bjorn Stroustrup, Bruce Ellis, and others contributed tools, libraries, and ideas. Within Bell Labs, Plan 9 gradually replaced Unix as the primary platform for operating systems research. The lab's new OS was growing up in the shadow of its own famous ancestor, and trying very hard not to repeat its mistakes. There's a pivotal moment in the Plan 9 story that the developers themselves have told many times. In the fall of 1989, Rob Pike and Ken Thompson were wrestling with how the Windows system should fit into their new design. They had already decided that everything as a file should be taken more seriously than Unix ever had. Not just disks and terminals, but networks, graphics, and even running processes would be exposed as file trees. They had also been exploring a single file protocol, which would later be called 9P for talking to any resource, local or remote. But there was a snag. It wasn't enough to mount distant file servers. To make the whole system truly composable, they needed to be able to mount arbitrary user space services, anything that could speak 9P over a file descriptor, directly into a process's view of the file system. According to Pike's and Thompson's own recollections, they each realized this, separately but almost simultaneously, while walking home from dinner one night. The next day, they compared notes and found they'd converged on the same idea. Around Thanksgiving 1989, they tore into the code. Over a few intense days, they rewrote key pieces, added new operations, bind, a new more flexible mount, and flush, and rewired the system around them. The 9P protocol that emerged in that burst of work is essentially the one Plan 9 used for decades, with later minor revisions. Out of that weekend came the three design pillars of Plan 9. Push everything as a file much further than Unix. Use a single simple protocol, 9P, to talk to all those files, and give every process its own private, malleable namespace, its own editable map of what the file system and by extension the whole machine and network look like. So what did using Plan 9 actually feel like beyond the slogans? Take networking. On Unix, creating a TCP connection means calling special socket system calls, working with opaque structures, and learning a dedicated API. On Plan 9, you just dealt with files. To open a TCP connection, a program would open the file, gnet-touch TCP to clone, read back an ID, then write a simple text command like connect host port into .net.tccp ID CTL. The data stream showed up as in net.tcp ID data. No magic socket calls. It could be scripted from the shell. Because all of this spoke 9P and because namespaces were private, you could do tricks that still feel startling today. Mount another machine's on-net into your own namespace, and suddenly your program's network traffic flows through that other machine's stack without the program being aware. Mount a remote dev-draw and dev-kbd, and you effectively have a lightweight remote desktop, a bit like VNC, built out of ordinary file operations. The graphical environment was built on similar lines. The Rio window system acted both as your window manager and as a file server, exporting a simple dev-draw interface. GUI programs didn't need to know whether they were drawing to a physical frame buffer, a window on a remote machine, or something else entirely. Editors like SAM and Acme, the RC shell, and Aleph, Phil Winterbottom's experimental concurrent programming language, all fit neatly into this world of composable tools. Aleph itself didn't last, but several of its ideas, especially around lightweight concurrency and channels, reappeared years later in Go, a language co-designed by Pike and Thompson. And then there was text. In the early 1990s, Ken Thompson designed UTF-8, a new way of encoding Unicode characters as variable-length byte sequences. In a famous weekend in early September 1992, Thompson and Pike converted the entire Plan 9 system, kernel, tools, fonts, everything, to use UTF-8. By the time an industry group, XOpen, met shortly afterwards to standardize a Unicode encoding, UTF-8 was ready, battle-tested in a real OS. After several years of internal use, Plan 9 finally left Bell Labs, at least in theory. The first edition was released to universities in 1992. It already contained most of what we now think of as Plan 9, the new kernel, the 9P protocol, SAM, the RC shell, the Aleph language, and full UTF-8 support. CPU servers were typically MIPS and SPARC workstations. PCs and custom terminals like Hobbit and Not acted as graphical front ends. In 1995, Bell Labs released the second edition more broadly, in a book and CD package distributed by the publisher Harcourt Brace. A site license cost around $350 and included source code, but AT&T aimed it mainly at embedded and research users, not at displacing mainstream desktop or server systems. Rob Pike and Dennis Ritchie both later remarked that no one expected Plan 9 to overthrow Unix by that point. The market was already moving towards standard Unix, Windows, and, increasingly, Linux. Commercially, it never took off. By early 1996, official attention inside AT&T had shifted toward a related but different system, Inferno, which they hoped could compete with Sun's Java platform. In the late 1990s, after Bell Labs became part of Lucent Technologies, formal support for Plan 9 dwindled. It remained a living research system, but not a serious commercial product. In 2000, something important changed. Lucent released a third edition of Plan 9, often nicknamed Brazil after an internal re-implementation effort, as a free download over the internet, under an open-source license. For the first time, anyone could fetch the full system and experiment. This third edition introduced a new graphics library called Draw, a flexible message routing service called the Plumber, and a simple package update tool named Wrap. Shortly afterwards, the team revised the 9P protocol into 9P 2000, loosening some old restrictions and adding features like batched path walks and better metadata. The fourth edition, released in 2002, bundled 9P 2000, a credential agent called Factotum, a secure key store named SecStore, and the Venti block storage server. On top of Venti, they built Fossil, a log-structured file server with snapshots and version history. Early ancestors of ideas you see today in snapshotting file systems and backup appliances. Although Bell Labs eventually stopped active in-house development, they kept hosting the master source tree. Plan 9 installations could update themselves straight from a public Fossil file server, pulling daily changes. In 2021, long after the original team had moved on, Bell Labs transferred the remaining copyrights to the Plan 9 Foundation. The code was relicensed under the permissive MIT license, and development resumed under community stewardship. Around it, a small but energetic ecosystem of forks and derivatives, including the popular 9-front distribution and newer research systems like Harvey and Jehani, kept the flame alive. By any normal metric, Plan 9 failed. It never built a large user base, never attracted mass-market software, and never threatened Windows, mainstream Unix, or Linux. The reasons are mostly prosaic. By the 1990s, Unix-like systems were already entrenched. Plan 9 deliberately broke compatibility with existing Unix software and APIs. Almost nothing could be recompiled without real porting work. Developers and companies faced a simple choice: adopt a clean but incompatible system, or use the Unix and Windows ecosystems where the compilers, databases, and customers already were. Licensing and timing also mattered. The early 1990s releases were expensive and proprietary, just as Linux and the GNU tools were exploding as a free Unix-compatible platform. Academic and hobbyist communities overwhelmingly rallied around Linux. By the time Plan 9 became freely available in 2000, it was a curiosity living in a world that had already standardized on POSIX. Inside Bell Labs, focus shifted to other projects and to surviving the telecom industry's upheavals. Plan 9 endured as a research toy and as the daily driver for a small circle of enthusiasts, but not as something executives were going to ship in volume. Yet, on a deeper level, many of its ideas quietly succeeded. Its snapshotting file systems foreshadowed modern backup schemes. Its RFFork system call, a flexible cousin of Unix fork, inspired similar primitives in FreeBSD and Linux. The 9P protocol shows up today in places like virtualized file systems and the Windows subsystem for Linux. UTF-8, born and battle-tested on Plan 9, became the de facto standard text encoding of the web and of modern operating systems. In that sense, Plan 9 is one of computing history's more interesting failures, the product that lost, while its concepts seeped almost everywhere. Today, Plan 9 survives in the hands of researchers, hobbyists, and a few stubborn daily users. Screenshots of its Rio Windows system, mouse-driven, stark, almost hand-drawn in its simplicity, circulate on blogs and retro computing forums. Distributions like 9-front ship Wi-Fi and USB support, new games and modern hardware ports, keeping the design usable on contemporary machines. But the real legacy of Plan 9 isn't the code still running. It's the mental model it offered. It showed that an operating system for a networked world could be radically simpler and more uniform than the layered special case APIs we mostly live with. It treated networks, graphics, and processes as interchangeable file trees glued together with one protocol in private namespaces, and then proved you could actually build and live in such a system. Even if you've never heard of it, you've touched its shadow. In the UTF-8 text you read and write every day, in container runtimes isolating processes with tailored namespaces, in Go programs using Go routines and channels, and in distributed systems which try, however imperfectly, to make location and implementation details disappear behind simple interfaces. Naming their ambitious new OS after a famously bad movie was a kind of hedge. If Plan 9 flopped, at least the joke was baked in. Decades later, the joke cuts the other way. The operating system itself became a cult classic, known mostly to connoisseurs. but the ideas that animated it escaped the B movie budget and went mainstream. In the long view of computing history, Plan 9 from Bell Labs looks less like a failed sequel to Unix, and more like a set of carefully crafted scenes that other operating systems have been quietly quoting ever since.